Last year, more electric cars were made and sold than at any point in history. And that's a good thing if you want the world to be cleaner, greener, safer and smarter. Fewer internal combustion engine cars, more electric vehicles. It's generally the way we want it to go. But there's a problem with that, because there's only so many mining companies in the world who are mining the raw materials you need for lithium-ion battery packs. There are only so many manufacturing companies who understand how to manufacture lithium-ion battery packs. And because of that, the prices of lithium-ion battery packs, while they're now finally starting to drop, are extremely volatile. All it takes is a supply chain issue or something else for those battery prices to soar upwards. And that's compounded by the volume of electric vehicles that are now being made, but also the sheer numbers of electric vehicles being made with truly massive battery packs. If you look back just 10 years, the Nissan Leaf was shipping from the factory with a 24 kilowatt hour battery pack. These days, 24 kilowatt hours, well, that's laughed at, and very few people would even consider buying a car with that small a battery pack. Instead, it's very common to see 100 to sometimes even 200 or more kilowatt hour battery packs in modern electric vehicles. Those electric vehicles are large, they are powerful, they have long range, they have impressive acceleration. And one of the reasons why those vehicles have such large battery packs is because the larger a battery pack, the longer the range your car can have, the faster it can charge, and the less stressed an existence it has during its life. It's a bit like the difference between having a Japanese four-cylinder engine that revs extremely high versus a lumbering V8 that will go on for decades with nary a problem. Automakers have then opted to make large vehicles with large battery packs so that they can get that massive range, that incredibly quick performance, and that long lifespan, as well as the rapid charging capabilities. But there is another way. It's possible to learn how battery cells work, take modern AI smarts, and model a solution that allows vehicles with smaller capacity battery packs to charge just as quickly as large battery pack vehicles, that allows vehicles to have a longer life on the road, and that even allows you to wring out a little bit of extra performance. That technology is Elysia, and it was born out of Formula E, and the company that has been working on Formula E technology since Formula E was first born. I am, of course, talking about WAE Technologies, who have invited us here to their engineering headquarters just outside of Oxford, UK. And I have a fantastic tour guide. Please welcome Joe Jones, who is going to tell us about all of the cool things that WAE has taken from Formula E and could put in a car that you might buy very soon. Joe, thank you for inviting us. I'm very glad that WAE Technologies sent us an invite and flew us over so we could see this firsthand.
It's great having you here.
We've been filming all day. There are some videos coming out in the next couple of weeks, one of them in a couple of months, that talk about some of the things that you've been doing. But tell me about Elysia, because it's not just a name, right?
No, exactly. I mean, you know, as you said in your introduction, right, for people like us who've been working in the electrification space for a while, you know, we've been waiting for that hockey stick moment, and 2021 really was that. I think sales more than doubled of electric vehicles, and that is a great thing, like you said. But it is true that comes with pain points, like you said, for the automakers and the battery manufacturers. You know, they're having to scale up production at a rate unlike anything they've ever had to do before. But also for the engineering teams as well, they're having to put out vehicles on the road without all that historical data. It's not like the combustion engine vehicles that have been on the road, being manufactured for hundreds of years. You know, the electric vehicle is still relatively new. We're only seeing those first generation of electric vehicles now starting to reach their end of life. but also for the people who lease those vehicles, fleet owners, delivery companies, for example, they're buying vehicles where maybe a third of the value of that vehicle is in the battery. But like you said, the battery is still not very well understood. And if we can understand the battery better, we can make batteries smarter, safer, last longer, and also extract more performance out of them. And that's what Elysia is all about. It's about using software, ones and zeros, to make batteries work for businesses, for the planet, and for us, for end consumers.
So Elysia is born out of Formula E, where in Formula E you want to get the maximum possible power out of a battery pack, because a lighter battery pack requires less energy to move it around the racetrack, more power that can go to the wheels to push the car along and help win the race. But it also means that the engineering teams and the pit crews are not having as many problems with the battery pack race after race after race. Tell me about the basis of where Elysia comes from and its race heritage.
We've been building, high-performance electric vehicle batteries for the last 10 years or so, serving many different electric motorsport categories, doing hypercars, all sorts of weird and wacky projects. And to do that, we've really had to understand cells, really from the inside out, right? We're not able to leave lots of performance and buffers on the table when we're supplying some of these series. But we still have to make batteries that are incredibly safe, that last the life of the series, and lots of that comes from the software, comes from the battery management system. And what Elysia is about doing is taking that technology, that know-how that we've developed over the last 10 years on the racetrack, but now making it available for basically every battery-powered device on Earth. And that could be an electric vehicle, but it could also be for stationary storage, for consumer electronics, for micromobility. We want to empower the world to get more out of lithium-ion batteries. But I guess the good news is that we think there's a huge opportunity there to do more with the silicon and the compute power that is on the battery management system. On any battery-powered device, you will have effectively a computer that looks after that battery, but also to make use of data. The fact that pretty much every vehicle that we will go and buy today is sending data to the cloud all the time, is connected in what was often called telematics data. So we think by doing more on the BMS embedded, but also in the cloud, we can make batteries safer, smarter, last longer, and get more performance out of them, doing more with less.
So before we meet with someone from your development team, tell me how battery management works today.
Yeah, absolutely. So, it's funny, when you say battery management, people always think of the hardware, right? They visualize something like this, the PCB. And of course, the electronics are super important. If I said anything else, the electronics team, I'm sure, would get very angry at me. But really, the hardware is just effectively a platform for the logic to run on. And the logic is the software, is the ones and zeros. But the BMS fundamentally is sort of the brain of the battery. It has to keep the battery safe, most important thing. But also it's about estimating the state of the battery, so something like state of charge, for example, and determining how that battery can be used. How are we going to allow that battery to be used? So when people want an electric vehicle, they want something that's going to travel a long distance, have good performance, and of course charge quickly. I'm sure when you speak to potential EV buyers, they always talk about fast charging. So those are some of the core functions, right? State of charge, so estimating how much battery I've got left or how much range I've got left. So that's often called SOC. State of power, so if I step on the gas for the next 5 seconds, how much performance is the BMS going to give me? So you can probably guess SOP, state of power, is what that's called. Fast charge, like we talked about, if I go up to a fast charger right now, how much power is the battery going to ask of the charger? So fast charge, no nice acronym for that one. And then on top of that, it has to do all of those basic safety functionalities, what's often called functional safety. So if a temperature all of a sudden spikes too high, or if all of a sudden what's low voltage starts becoming high voltage, that's when the functional safety elements know to jump in and switch off the battery effectively. And then the last bit, which is maybe the biggest sort of enigma, if you will, is health. And what one person talks about when they're talking about battery health versus what someone else talks about when they mean battery health can be very different things. But we'll come back to that, because that's actually what sort of ties all of this together. So state of health, or SOH, is something that's super important within the battery
management system. And of course, everything is
system.
hidden inside the cell. You can't physically see the cell. It's just a cell.
Exactly.
You put a wire on one end and a wire on the other and connect it to a circuit, and power flows. And that's basically where the battery, that's all the battery does.
Exactly. And actually inside a lithium-ion cell, well, you could look at it and say it's a component. There's this whole universe of physics and chemistry and mechanics, but like you said, it's unobservable, it's hidden away. And that's really why battery management is no simple thing.
Which is where the world of software and engineering comes in. I know one of your colleagues, Melissa, is going to come and join us.
Yeah.
Melissa, you are the lead developer on this. Tell us how programming can help make this smarter.
So, as Joe has said, typically in industry, they view the cell as a component. So this is just a black box. It has simple usage limits where it keeps the battery safe, but it's often quite unoptimized. So what we do is we treat it as a system, and we develop these mathematical models, these battery cell models that really model the behavior of the cell. So the voltage response when Joe puts his foot to the ground and accelerates his EV, or when you're driving and you see the cell temperature heats up. So all of these are encompassed within these cell models, and these cell models are then applied on the various BMS functions that Joe had described.
And you can reiterate in software far quicker than you can using real physical world testing, right?
Yes, there is. So the virtual world, in digital twins, which the team will talk about later, can enable this iteration, and even for us on the embedded platform, among our motorsport programs and history, have enabled us with these models to iterate quickly and develop the software that you now see on our major programs at WAE Technologies.
And it's used on everything from race cars through to mining trucks, right?
Yes, correct. So all the way from race cars to the giant trucks that in Australia all utilize these functions. Going back to SOC. So SOC is a measure of how much is left in the battery, right? So like a traditional internal combustion, which is a fuel tank, and you want to know how much is left in an EV, you also want to know how much is left in the battery. But unlike a fuel tank, which has a gauge that you can measure the levels within this fuel tank, you can't really do that with a battery, and we have signals and measurements that we can take, like voltage, temperature, current, that we can infer SOC, but the state of charge is estimated, and it's really the accuracy of the SOC that really enables us to utilize more of the battery packs that we have. And in our flagship programs, we're using 98% of the total range, which with errors of like 1% to 2%, and it really allows us to push the technology. And this, as part of this SOC accuracy, is also with our models.
And I think on that, the impact for industry, for those road cars that we all go and buy, that means doing more with less. means not over-engineering batteries, having less, reserve in the tank while still being reliable, right? While still, when I see 12% left, that means I genuinely do have 12% left in the tank, rather than having to add these big buffers at the bottom end of a battery and leave, 5, 10, 15% unused.
And traditionally, the way that batteries have been kept safe is to have those those massive margins, because traditionally speaking, batteries become very unpredictable at the lower end of their state of charge. The delta in terms of voltage, the voltage sag, regardless of whether you are flooring it or whether you are just turning an additional load on somewhere in the cabin, can make a difference to how that battery performs and behaves. It's also, I think, one of the reasons why OEMs very often give up when you get to 10% remaining. They just go, you need to plug in now. Is that something that you can help with Elysia? You can have a more accurate state of charge at the lower end?
Yeah, so with our extensive testing and understanding of these components that are within a cell, that we can better model the behavior, and going with that, going back to what's traditionally done, it also impacts the power that we can provide at those low states of charge, because traditionally, again, extensive testing is done, which is they test cells and determine the power at all the different conditions that the cells can be used at, and they create this giant matrix of data points that they can extract and understand this is what the cell can do at this temperature, for example. But really, that's really inflexible, right? So if we don't test all conditions, we need to understand what is happening within the cell, and again, the recent history will affect the voltage behavior and what's happening with these components. An analogy a comparison that we like to give is, how in terms of power, we can think of it as, your time to do a 100-meter sprint. But that just how much you can do a 100-meter sprint depends on what you've done previously. Did you just run a marathon? It'll change what it was. Will change your 100-meter sprint time, and equivalently will change your power. So it's this understanding of the components and what's limiting, as well as the recent history that allows us to have better SOC estimation, as well as be able to apply power across a wider range of the cell usage.
Tell me about how you're able to wring more power out and allow the car to unlock more power for acceleration, for rapid charging, power ingestion, I suppose. How is it possible to do that without changing any of the major hardware in the battery pack? Because I know a lot of people are going to be watching this and going, this sounds weird.
I mean, really, as Melissa said, it starts with understanding all the different potential limiting factors within the cell. So instead of simply testing the cell as a black box, we actually try and model the performance of all the different components within the cell that collectively determine what that can do. So in the case of fast charge, like you talked about, what is fast charging actually, right? It's the movement of lithium ions from one side of the battery to the other. In the case of fast charging, from the cathode into the anode. But actually how fast we can move those lithium ions depends on a number of things, like Melissa talks about. It could be, the age of the battery has a huge impact as to what it can do, but also the temperature, right? If it's cold outside, that will often have a big impact in terms of how quickly we can move those ions across. So if we model all those components within the cell, that allows us to optimize for the fastest charge time possible without damaging the cell. I mean, an example of this that we worked on recently was for an electric hypercar, and we managed to get a 9.5-minute fast charge time from 5% to 80%. And when we compared our fast charge algorithm to a traditional stepped fast charge algorithm, which is done by lots of testing, like Melissa talks about, we actually got 60% more life for the same 9.5 minutes. I mean, this is most evident, when we go and plug in an EV, often you'll plug it in, you'll get that promised 150 kilowatts until, maybe 35% state of charge, and all of a sudden it drops down and it becomes this sort of, stepped, very kind of analog or digital sort of profile. We actually ramp up dynamically up and down the power of the cars demanding from the charger, depending on exactly what we think the relationship is between the anode and those lithium ions.
Now we've talked a little bit about the software. I'd love to know a little bit more about the overarching hardware. And because, ironically, the reason that you and Melissa were wearing two microphones is we're having microphone issues today, which we think might be battery-based.
Yes.
So Melissa's had to nip out. Let's talk to Tim, who is the lead of the project, right?
Yeah. So Tim's technical lead.
Yeah. So we're talking about state of health, and really that is everything that ties this together. So, all of the algorithms we've talked about, be it fast charge or power limits, are very, important at the beginning of life, but really that battery is changing all the time. It's degrading in complicated ways. So really we like to think of the Rubik's Cube analogy in that really you can't solve a Rubik's Cube one side at a time. You need to see it as one holistic problem, and this is really what battery management is all about. It's about thinking about the health adaptivity of everything we do when we control a battery. And like Joe said, health is different from one person to another, and actually it's multifaceted. It's in the same way that you or I wouldn't describe our own health in one number. It's actually multidimensional. There's lots of parts to that. And really that is a complex problem, and people are trying to get to grips with it. And devices like this, the telematics devices, is really about how do we use this data? We're collecting all of this data. Is there something we can learn from it to tell us more about how we should adapt to the way we use our batteries as they degrade?
How do you even start using AI modeling to figure out an ideal, well-behaved battery pack? Because we're talking about going right down to the subatomic level within the battery pack. We're talking about looking at the actual individual structures of each element as found in the battery pack at a slightly larger level. We're talking about the micro fractures that happen within the anode and the cathode when things go wrong. We're talking about ion passage through the cell itself, ions getting stuck in the cathode or the anode, and suddenly the battery cannot produce as much power as it used to, which is part of the aging process, right? So how do you model all of that and then realistically go, I know exactly that this battery at this point in history is at this point in its life cycle or its...
Yeah, I mean, that's the holy grail. I mean, a lot of people will take this data, and the instinct is to throw it at big AI models. The problem with that is that there's a lot of variables here, and they're collinear. There's things that relate to inputs and outputs. It's hard to really separate the signal from the noise, what's correlational, coincidental, if you like, and what's causational. And it comes back to the way we consider a cell a system. So we model each part of that cell, and we can see which is the limiting factor within the cell. So it's really about taking the fields of data and AI, but also the fields of the first principles, the electrochemistry, that explains most of what we see, but not everything. And that's why you need the flexibility of the AI, but you need the interpretability of the kind of physics-based modeling, if you like.
So obviously I alluded a bit earlier that when a battery cell starts to feel unwell, when there are cracks, when there are things stuck that shouldn't be stuck, that degrades the cell over time. And every battery throughout history slowly loses the ability to store charge. Yes, there are batteries, original batteries that are over 100 years old that still carry a charge, but they're not being asked to provide the amount of power that a modern EV is providing. So how do you go about figuring out how healthy whether a battery is degraded, how long it's got left in its life?
Yeah, I mean, battery degradation is a bit of an enigma. It's non-linear. It can be very different from one cell to another. It could be to do with difference in production or the way that the history of that battery, the way it's been used. It might be helpful actually to draw something out here. If this is capacity, this is time. Degradation often looks something like this with time, so it's relatively linear. Another cell, might be similar at the beginning and kind of following this trajectory, but then at some point it kind of falls off a cliff, and we call this a knee point. The reason for knee points is a big issue within this industry, and these are the cells we care about. These are the ones that die early, and ultimately the battery is limited by the worst cell in that system.
So is that like the song, "Only the good ones die young"?
Pretty much. So I mean, for us, it's really about what is causing this, and like we said earlier, this battery is not just a component; it's a system. And what's actually happening behind the scenes in some cases is there is something happening, some kind of degradation mechanism that is not yet limiting, but eventually becomes limiting to the capacity that we can extract from that battery. So in other words, there might be some component within this battery, maybe the anode or the cathode, that is being damaged behind the scenes, but is already in excess and eventually becomes limiting.
Identify it. You can identify this by using other data that you've captured.
If you know where to look in the data, these features can be detected, and it means we have some insight into which cells will die early. There's an example in a slide here. So this is an example of a battery test we did in the lab. These are the first data points of that test. So we had 3 different cells that we tested on the exact same cycle. So it's an automotive use case in a 10-degree climate. And so you might see this and say, well, actually, let's draw a line through that. And this is what we see here. You could say, looks like we're going to get to a specific state of health in a certain number of cycles. But when we continue that test further, we see that one of the cells continues on that trajectory, but 2 of them go through this knee point. And this is really interesting because they're from the same box. They're cells from the same batch. They're in the same thermal chamber. They're running the exact same duty cycle. So what's really going on here? Well, it's what I said before. Certain differences from one cell to another means that one is over a tipping point and one isn't, and a bottleneck starts to ensue, which causes this knee point. So what we do is we track these various components of the cell and their ability to play ball, if you like, to deliver capacity, and we can see very early which ones are likely to fail early and which ones are on a good trajectory, as we see with the yellow one.
And that allows you, obviously, in the race car world, to make sure that your pack is absolutely optimum before you actually head into the race, because you've been able to identify any weak cells long before they actually become a problem in the race.
Exactly, yeah, and even in the kind of race car world, we have algorithms that can tell us which modules or which cells should be replaced so they don't fail on track. And we can use this in screening and manufacturing of which cells do we want, which cells are more likely to fail. So there's endless opportunity here. But I think the takeaway from this is that all cells are different. So even if they're from the same box, used in the same way, there's no simple model that can describe every single cell. And so this is where this idea of data from the battery management system going into the cloud can work, because we can look at every single cell independently. So each cell within the battery, within each vehicle, for the whole fleet, is modeled independently with its own digital twin. So we can track the prognostic certainty of is that going to fail early? Is it going to last a long time? We can look at the performance, and we can look at the life prognosis for that cell.
And as the digital twin ages with the battery pack, its characteristics will also change.
Exactly.
Based on the data that you're bringing back in.
Exactly.
But I think the other thing that's worth saying is life is small changes in behaviour can have a huge impact on life. If we predict that a cell may go through an E point, quite early on into its life, that doesn't mean it's all doom and gloom. That doesn't mean that that cell inevitably will have to go through that knee point. That there can be small changes, whether that be through maybe changing a fast charge curve if you're the car manufacturer and doing a software update, or if I was a fleet owner operator, let's say I have lots of electric delivery vans, it might be small operational changes like charging up to 90% rather than 100% when I park overnight. Those small changes, which may seem insignificant, can literally change the potential life of a vehicle by years. So we can get rid of those rare edge cases where batteries don't meet the life target.
And I'm guessing if you can better predict the lifespan of the vehicle, it also means fleet companies have to worry less about paying off the financing of their vehicles in a short period of time.
Yeah.
Because they can extend the amount of time that they're paying that investment off. Their ROI, effectively their period,
Absolutely.
gets changed. But also for rental fleets, who are currently putting ridiculously high valuations on battery packs after a 3-year, 36,000-mile lease, because they're worried that when they get the car back, the battery is going to be completely knackered and they're not going to be able to sell it on.
Yeah, exactly. It's right now, battery life is still an unknown for so many people in industry. So what we're taking now is that capability, the technology proven on the racetrack, and basically empowering not only the car companies, but any fleet owner or lease co to understand battery health, battery life, and make batteries make sense, basically.
So before we close out, tell me how Elysia will be offered. OEMs, individual fleet operators, heck, even somebody who's looking to buy a new car.
Yeah, exactly. I mean, that's so in terms of taking all that data and turning it into actual insights, right, actionable changes, that's why we are creating the Elysia cloud platform. So the Elysia cloud platform, we've actually made you a demo account, is effectively turning all that insight into stuff that's, and anyone can understand. It's not designed by engineers for engineers, it's designed by engineers for anyone who is effectively invested in battery health. So here we've mocked up some data because we can't show you any confidential customer data. But here, for example, we might have an example fleet, maybe it's in Norway, where actually a percentage of vehicles may not meet life, or at risk right now of not meeting life. What we're able to do with the cloud platform is actually dive into that. Let's pick maybe the vehicle that's most at risk now of not meeting life. Maybe it's going to fall short by a year, and we can not only see, okay, its future health trajectory is X, but actually why is that, and what can we do about it? In this case, fast charge usage relative to the rest of the fleet is actually taking off a year and a half's worth of life. So what we can do with the cloud platform is not only alert a customer to it, but say, hey, the potential intervention here is, lithium plating is a risk. Maybe you should look at changing your operations to improve that. And that could be for a fleet owner operator, like you talked about, or it could be for the car manufacturers to look at doing software over-the-air updates.
I mean, in this case, we've seen this vehicle has done a lot of fast charging, and the model is saying that that's the cause for not meeting life targets. But in this case, we've got a warning as well about lithium plating, which is really when you charge too fast at a low temperature. This is a problem for life, but it's also a problem for safety, or can be a problem for safety, because that lithium that can't get into the anode is essentially in a traffic jam. It can't get in. It's this kind of anode structure wants to accept it, but it's too much, too fast, and it ends up plating on the surface, and that can effectively grow and pierce through the separator and cause a short circuit. Which kind of takes us on a little bit to the safety.
Probably the last point, which we've not really talked much about.
Right,
Yeah,
so you've got dendritic build-up caused because of this lithium plating,
exactly,
which shorts out your battery, and then you don't have a battery anymore.
Yeah, exactly. So it is very rare, but when an EV fire does occur, it really damages consumer confidence, and really it's about how do we use data to predict these thermal events so that they don't happen in customer vehicles and that they can go into service well ahead of that problem. So we take kind of an interesting approach to this. So, traditionally, a big AI model would take the failure data, and they would be kind of training models to try and predict what is common about that failure. So it's got all of this data, it's trying to train a model to say, what is it that causes this fire? The problem is there aren't very many data points. Hopefully there aren't any anyway. If there are, it's already too late. So you end up with something called overfitting, which is where effectively it finds correlations that aren't necessarily causational, coincidences, if you will.
It's the equivalent of Googling, I have a headache and there's a weird rash on my arm.
Yes, exactly.
And then suddenly you've got this super rare disease and the doctor just goes, you were sleeping on your arm.
That's exactly it. And this is what this person at the bottom of the triangle is trying to represent. It's a little bit confusing. You have this opaque, one-dimensional rating of risk. What we do is really understand the underlying science. So we develop these prognostic algorithms from first principles, what we call a bottom-up approach. This means that we have these different metrics we can aggregate together to understand the risk of a failure mode, which means we've already predicted a failure risk before it's occurred. That means if any failures do happen, it's really just confirming or validating the model. And we can then take some top-down iteration to this, which is where, given what we know about what has happened, what failures may have already occurred, or tear down data, etc., we can start to tune how we use the metrics we have that relate well to the failure modes that we know about. And this is really a key to our ethos, if you like, about how battery intelligence should be done.
And moving forwards, this platform is going to be available to a whole range of different people in a whole range of different ways. So you've got your automakers, you've got your fleet operators, but there's a way to package this for individuals as well. If someone's buying a car and they want to know if the battery is in good health, how could this help them?
I mean, so exactly that idea of transparency for battery health is going to become more and more important as more and more electric vehicles go into the second-hand market. So by having effectively a third-party validation tool that will enable those dealerships, those fleet owners who are then selling those vehicles on into second life applications, effectively a legitimate, transparent evaluation of what is the true health of that battery, what has it done, but also what will it be able to do in future. So that could be great for a second-hand customer, or it could be great if you're taking those batteries and putting them in another application like stationary storage, for example.
So you've got this software solution that's going to be really useful to a huge part of the automotive industry, from automakers through to fleet operators and beyond. What's the end goal of this, though?
So really, it's about making electrification make sense for more people. That means making batteries that are right-sized, right? Not having to over-engineer batteries around the unknowns, but also the end impact meaning that, lease costs and vehicle costs for people like me and you is lower, that electrification is more compelling. So whether it's an individual like myself or whether I'm a bus operator who's looking to finance a vehicle over the next 7 years, or is it 10 years, that's how we can make electrification make sense for the masses.
It's very exciting, and I hope that it reduces resource use and allows us to have smaller vehicles with smaller battery packs that charge just as quickly as the big ones. I've been having this ongoing discussion with people in North America about how much we don't need massive battery packs. It can be quite frustrating. Thank you very much, Joe. Thank you, Tim. And thank you also to Melissa. It has been a wonderful trip. Thank you again to WAE Technology for inviting us and for flying us out here and putting us up. And I'm now going to go and sleep because I've got terrible jet lag. On that note, we are done with today's video. If you do have comments, drop us a polite note in the Discord chat room on Mastodon, or if you are a Patreon supporter, in the comments there. If you want more, subscribe, hit the bell and follow the links to support us regularly with a YouTube membership or a Patreon subscription. You'll also find links to our Ko-fi, Bitcoin and Swag store, as well as that aforementioned Mastodon server. Scrolling on my right in front of the Blade Glider is the list of amazing charged up supporters. And shout outs go out to our self-driving tier supporters, Paul Nelson, Mike Weeder, Denny Hyde, Linda Irish, Lance Schall, Mark Eggleton, Cyprien Laplace, John Trammell, Alan Tupper, Chris Maxwell, Brian Newton, Bennett Elder, Andrew Martin, Sean Tucker, Pedro Mura Pinheiro, Kyle Hodgson, Tony Moss, Brophy Wolf, Kyle Fox, Hay Esker, Tazla in the Gong, Dan Blair, Peter Dillinger, Gordon C., Stefan Fremgen, Stephen Williams, Regine Fellows, Chris Centaur and Jim Burness. And finally, out of this world thanks to our top tier supporters. They are the lovely John L. Henderson, Clay Witt, CPU Freak 101, John Lyons, Kevin Boroughbridge, Anonymous Freak, Andrew Glenn, Joe Hughes, Dave Kitchen, Joe Bresney, Nigel S. Matthew, Drobnak, Eric Knack, Paul Conway, Stephen O'Donoghue, JP Fagerback, Reggie Watts, Marcel Ward, Robert Flannery, Aaron Hahn, Rory Litwin, Ellery Hensley, Will Graylian, and of course, last but not least, Ian. Don't forget that we make videos every Monday, Wednesday, Friday and Saturday on this channel, at least when we're not travelling, which we've been doing a lot lately, and also over on Sunday on Take 2. You will find the Sunday Musing and also the chicken and garden update, because everyone needs to know about chickens and gardens, whether they are mine or whether they are the lovely Kate Walton Elliott's. We both have them. It's a thing. It's not a British thing. It's just a thing. I hope you enjoy the rest of your day. I'll see you soon. And as always, keep evolving.